Another type equation that we're going to be using are called quadratic surfaces. Quadratic surfaces are defined by the general quadratic or secondary equation with three variables. So we have our ax squared plus by squared plus cz squared, and then we have all possible combinations, xy terms, xz terms, yz terms, x terms, y terms, z terms, or just constant values. So this is your general quadratic equation with three variables. The graph is what's called a quadratic surface. Now, to graph these quadratic surfaces, what we're going to look for is three things. We're going to look for first intercepts, which are going to be points where the surface intersects the coordinate axes. Now, if you want to find the x-intercept, you'll let y and z both equal to 0. The y-intercept will be points where the x and the y and the z are both 0. And the z-intercept, where it crosses the z-axis, will be where x and y are both equal to 0. Now, the next thing we'll look at is traces. Traces are going to be with different planes. So we can look at where the surface intersects z equal to 0. That gives us the xy trace. Or we could use any z value. So z equal to some number, some constant value. That's a plane that will be parallel to the xy plane. Likewise, the trace with the plane y equal to 0, remember y equal to 0 is just your xz plane, so that would be the xz trace, or y equal to any constant would be a plane that's parallel to the xz plane. And then also x equals 0 gives us the yz trace if we're intersecting the surface with the equation x equal to 0, which is the yz plane. So x equal to 2 would be a plane parallel to the yz plane. So once you get the intercepts and the traces, sketch a couple of the traces in parallel planes, like what we did on those last examples, and then just draw curves that go through those traces to fill out the surface. So sketch the surface defined by the equation x squared over 3 squared plus y squared over 4 squared plus z squared over 5 squared equal to 1. Let's find x-intercepts. That's where this surface intersects the x-axis. So we'll let y and z equal to 0, and we'll have x squared over 9 equal to 1. So x squared is equal to 9. So x is equal either 3 or negative 3. So that's the places, the points 3, 0, 0 and negative 3, 0, 0, where it crosses the z-axis. So we've got here, wait, that was the x-intercept here and here. The y-intercept, we'll let x and z be 0. So we'll have y squared over 16 equal 1. So y is plus or minus 4. So that's where the graph crosses the y-axis. So the points 0, 4, 0, and 0, negative 4, 0. Z-intercept. Let x and y both be 0. You'll have z squared over 25 equal to 1. So z is plus or minus 5. So that's the points 0, 0, 5 and 0, 0, negative 5. So now you have where the graph of this ellipsoid crosses each of the coordinate axes. Now let's look at traces. The xy trace is where you're finding where it intersects the xy plane, which is the equation z equal to 0. So letting z equal to 0, we have x squared over 3 squared plus y squared over 4 squared equal to 1, which is an equation of an ellipse. The ellipse will have The major axis will be along the y-axis, and the minor would be along the x-axis, so length 3, and that's exactly this ellipse that we have drawn here. Now, if you want to find an ellipse parallel to the xy plane, you could let z be, let's say, 5. So this will be a plane parallel to the xy plane. And you'll have x squared over 9 plus y squared over 16 plus z squared, so plus 5 squared over 5 squared, so plus 1 equal to 1. Well, what that's giving me is x squared over 9 plus y squared over 16 equal to 0, which ends up only being the point 0, 0, and that gives you this point up here. You can see that intersecting this ellipsoid with the plane z equal 5 is only those 2 points. Z equal 5 is just this point up here. If we did a z value bigger than 5, you'll see that there's no points at all. And when you put z equal 5 or something bigger than 5, you're going to end up with x squared over 9 plus y squared over 16 being negative, which has no solutions. So you can see if z is bigger than 5 or z is less than negative 5, there will be no points in that trace. So now let's look at, as long as z is between negative 5 and 5, you'll get an ellipsoid like here or down here. Okay, parallel to the YZ plane. So that's the YZ trace. That'll be when you have x equal to 0. So we will have y squared over 4 squared plus z squared over 25 equal to 1, which again is just an ellipse. So parallel to the YZ plane, then that would give us this ellipse here. Okay, so we have an ellipse going in that direction also. And now the last one, parallel to the XZ plane, that's where the y is 0. So we would have x squared over 9 plus z squared over 25 equal to 1, which again is another ellipse. So parallel to the y-axis, or the XZ trace would be look something like this one. Actually, I may have got the wrong one there. It's this. Actually, it's this one right here. Okay, and any plane parallel to that, the XZ plane, will just give us an ellipse down here. Okay, so if you can see if the traces in each of the 3 directions, parallel to the XY, the YZ, and the XZ plane, give an ellipse, then you're going to have an ellipsoid. Okay, this graph, let's look at the intercepts first. So the x-intercept is where the y and the z are both 0. So you're going to have 0 equal to x squared over 16. So x is 0. The y-intercept, x and z are both 0. So you're going to have 0 equal to y squared over 4. So y is 0. And the z-intercept, you'll have z equal to 0. So the only intersections with the coordinate axes will be at the point 0, 0, 0. Okay, let's look at the traces. The xy trace, letting z equal to 0, we get 0 equal to x squared over 16 plus y squared over 4. The only way this equation can be satisfied is if x and y are both 0. So parallel to the xy plane, when z is 0, that's the xy plane trace, is just that point. Let's look at another plane. Let's look at z equal to 4. that's parallel to the xy plane. So we would have 4 equal to x squared over 16 plus y squared over 4, which again is an equation of an ellipse. We could rewrite this by dividing everything by 4 to be x squared over 64 plus y squared over 16, and you can get that trace. It's going to have a 8 would be the distance down the x-axis and 4 down the y-axis, but it's an ellipse like that. That's parallel to the xy plane. So the yz trace, that's where x is 0, you would have z equal y squared over 4, which is just a parabola. So parallel to the yz axis, you get a parabola. Now the xz trace. Let the y equal to 0. You have z equal to x squared over 16, which again is a parabola. So parallel to the xz plane is another parabola. So now if we found some other traces, so we saw that the trace in the xy direction, parallel to the xy plane, was going to be an ellipse each time. Then what we've got is we've got an elliptic paraboloid. So cross sections horizontally will be ellipses, but with the other two planes, they're parabolas. So now let's look at this surface. X-intercepts. So x is either 2 or negative 2. So that gives us the points 2, 0, 0, negative 2, 0, 0. Y-intercepts. We would have y squared over 9 equal to 1. So y is either 3 or negative 3. And z-intercept. Well, that means z squared is negative 1, which has no solution. So that means that this surface does not intersect the z-axis at all. Okay, so now let's look at some of the traces. The xy trace. If z is equal to 0, we have x squared over 4 plus y squared over 9 equal to 1, which is an ellipse. Let's see this ellipse right here. Let's look at some other traces parallel to the xy plane. So z equal to, let's say, 2. So we would have x squared over 4 plus y squared over 9 minus 4 equal to 1 equal negative 3. There's no solutions to that. So the xy plane Now let's look at the graph of y squared over 4 plus z squared equal 4x squared. Intercepts would be 0 equal 4x squared, so just x equal to 0. Y-intercept, that's where x and z are both 0. That's just at y equals 0. And the z-intercept, where x and y are both 0, you get z squared equal to 0, so z equals 0. So again, the only place where they intersect the axes, the coordinate axes, are at the point 0, 0, 0. So now the traces. XY trace, we have y squared over 4 equal to 4x squared. Now this is the line y squared equal to 16x squared. It's not a line, it's two lines. So this would be y equal plus or minus 4 times x. So in the xy plane, you have two lines, y equal 4x and y equal minus 4x. Now the YZ trace, likewise will be y equal plus or minus 2z. So it'll be two intersecting lines in the YZ plane. So y equals 2z. Okay, and now let's go ahead and just look in the XZ plane. Okay, this one is the plane. I messed up on the other one. 2x. Okay, so this is two intersecting lines. Let's go back to the one previous to here. This right here only has a solution of 0, 0. Didn't look at that close enough. Right, the only way this will be satisfied is if x, y, and z are both equal to 0. So that means the point 0, 0, 0 is the only intersection with the YZ trace. So we've just got a single point there. But now let's look at this case, and we're going to look at lines parallel to that. So let's look at x equal to 1, and then maybe x equal to 2, or x equal to negative 1. Okay, if x is equal to 1 in this equation, we'll have y squared over 4 plus z squared equal to 4, which is just an equation of an ellipse. So we have y squared over 16 plus z squared over 4 equal to 1 is our standard form. We'll have an ellipse, and notice as that x gets bigger, then we'll be dividing by bigger numbers to get these numbers bigger. So you're going to have a larger and larger ellipse as the x value gets bigger. So we'll have ellipses, x is getting bigger, so we're going to have ellipses coming out this direction and this direction. And likewise, if the x is negative, it's going to be the same type thing. So we're going to have an ellipse this way, and we'll have an ellipse this way. Okay, so what happens is we have intersecting lines passing through here and here, or across the top ones of here and here. I didn't draw that right. I should have been going across there and there. But in this direction, we will have ellipses getting larger and larger. So what you've got here is you've got a cone. It's called an elliptic cone, where it's going out this way. This is the origin. Okay, so the cross sections with planes parallel to the YZ plane will be cones. Okay, now this is a graph of, this is a bunch of the standard forms of the equations and what the names of these surfaces are. So here's your hyperboloid of one sheet that we graphed, elliptic paraboloid, here's your ellipsoid, hyperboloid of two sheets where they separate, so in the middle there's no graph. So um, the elliptic cone is what this last one that we graphed was, and this is the standard form. So that's where you have the x squared, the y squared, and then the z squared on the other side. If you changed which one was isolated on the right side here, it would be parallel to a different, the axis would be parallel to one of the other axes. So the one that we had before actually was down the x-axis. Let's go back and look at that one again. Notice the x was the one isolated over here, so it was parallel to the x-axis. That was your axis for that cone. So you can see, what the traces will be in each of these planes, and it gives you an idea of what the graph's going to look like. So, kind of be familiar with each of these shapes, but you can also tell by looking at traces is what the graph will be.